This is Unit 7, Lesson 4, Conditional Probability. Conditional probability is simply the probability that event A will occur based on the condition that event B has already occurred. Conditional probability notation is written like this: the probability of A given B. So B has to happen first, and then we'll calculate the probability of A happening based on the fact that B has already happened. And we do that using this formula right here, the probability of A and B divided by the probability of B. Example number 1 says the probability that it is a Friday and that a student is absent is 0.03. Given there are 5 school days in a week, the probability that it is Friday is 0.2. What is the probability that a student is absent given that today is Friday? So we set up the problem, the probability of a student being absent given that it's Friday. And so the first thing we do is we calculate the probability of someone being absent and it being a Friday. So those two things have to occur at the same time, divided by the probability that it's Friday. Now these two probabilities were already given to you, so you don't have to actually calculate the probabilities. You just need to plug them in. So the probability that it is Friday and a student is absent is 0.03, and the probability that it is Friday is 0.2. And then all you'll need to do is divide, and you'll find that 0.03 divided by 0.2 is 0.15, which is 15%. So the probability that a student is absent given that it is Friday is 15%. The next thing that you're going to need to be able to do is actually write the probability statement. This is the probability statement. And this is where students tend to get tripped up, because you have to decide which event happened first and which event is going to happen second. So this problem says a math teacher gave her class 2 tests. 25% of the class passed both tests and 42% of the class passed the first test. What percent of those who passed the first test also passed the second test? This one should be pretty simple, because what had to happen first? Well, you had to take the first test. You had to pass the first test before you could pass the second test. So we're going to look for the probability that you passed the second test given that you passed the first test. So we're going to set this up, and we're going to look for that intersection, the probability that you passed the first test and the second test. And we're going to divide by the probability that you passed the first test. For this problem, because these numbers were given to you in percentages, you need to go ahead and change those to decimals. So that's going to become 0.25. That's going to become 0.42. And the percentage of people who passed the second test and the first test was 25%, so 0.25, divided by the percentage of people who passed the first test, which is 0.42. And as a decimal, 0.25 divided by 0.42 is 0.595, and as a percentage is 59.5%. When you're working these problems and you do the division, go ahead and round to the thousandths place, round to that third decimal, and then when you multiply by 100, you'll have a percentage that is already rounded to the nearest tenth. So if you'll start by rounding your division, whatever you divided, to the nearest thousandths place, you'll have a really nice even terminating decimal for your percentage. So now comes the part where we're going to have to actually decide which is the first event and which is the second event based on how the problem reads. So for example number 3, the question is, for a standard deck of playing cards, find the probability that a red card randomly drawn from the deck is a jack. So you got to start by writing that probability statement, the probability of A given B. And you have to decide which one of these things happened first. So we want to look at the part of the problem that says probability that a red card drawn randomly from the deck is a jack. We're going to focus on just that part of the question right now. We need to decide what happened first. Well, the probability of a red card. So that means you're already holding a red card in your hand. That's already happened. Now, after that, what's the probability that that's a jack? So if you've already got the red card in your hand, that happened first. So you're going to say, what's the probability that you have a jack given that you already drew a red card? So you're going to have to read the problem and think about which one of those things happened first, and then decide from there what's going to be the part that happens second. So then we're just going to plug the numbers in. So we need to do the probability of a jack and a red. So we need to know how many, the number of jack and red cards divided by the number of red cards in a deck. So how many cards in a deck are jacks? Well, there are 4 jacks in a deck. How many of those jacks are red? There are only 2. So there's 2 red jacks in a deck of cards over 26 cards that are red. And you can go ahead and reduce that to 1 over 13 if you want to. And as a decimal rounded to the nearest thousandth, that becomes 0.46, so 0.046. And as a percentage, that's 4.6%. Take the time to make sure you understand which event happened first and which event happened second in order to write that probability statement, because everything revolves around if that probability statement is written correctly. If that probability statement is incorrect, your entire problem is just going to go downhill from there. Example number 4. We talked about this in class the other day. We want to go ahead and finish this chart, and this is actually the chart we used in class. There were 110 high school students surveyed and asked whether they prefer cats or dogs as pets. What is the probability that a student prefers dogs given that they are in the 12th grade? This problem goes ahead and tells you which one of those needs to be the first event and which one needs to be the second event. So we want to know the probability that a student prefers dogs given that they're in the 12th grade. So if you can find that keyword given, because remember this straight line right here is where we say given, the probability of dogs given that you're in the 12th grade. If you can find the word given, use it. And remember that the given always comes second when you write the probability statement, which is very strange because it's the thing that actually happened first. And then we're going to say, hi, what's the number of students who like dogs and are in the 12th grade? Divided by the number of students in the 12th grade. So we come over here to our table and we find the 12th graders in this row right here. We find the dogs in this column right here. And where they intersect is our number of students who prefer dogs and are in the 12th grade. So there are 30 students who prefer dogs and are in the 12th grade. And how many students are seniors? So we look at this, we go all the way to the total, 30 students are seniors. So 30 out of 37 as a decimal is 0.812. 811, don't know why I rounded weird like that, which is 81.1%. Now in these last 2 problems, we're going to add something to them. We're going to add independence. We need to determine if events are independent of one another. And to determine independence, you take the probability of event A, and the probability of event A should be equal to the probability of event A given B. So we'll plug things into this formula after we plug it into the conditional probability formula. So our first example on this section is for a standard deck of cards, find the probability that a queen randomly drawn from the deck is a diamond. So the key is a queen randomly drawn from the deck is a diamond. Let's make sure that we get our probability statement, our conditional probability statement, in order correctly. So what happened first? A queen randomly drawn from the deck. You already have a queen in your hand. Now, what's the probability that the queen in your hand is a diamond? So the probability that you have a diamond given that you've already drawn a queen. And that's going to be equal to the number of cards that are a diamond and a queen at the same time divided by the number of cards that are a queen. So how many cards are a queen and a diamond at the same time? Well, there's 4 queens and only one of those is a diamond. So there's 1 diamond queen. And how many queens were there? Well, we just said that there were 4 queens. So 0.25, 25%. So now we need to determine if these two things are independent of one another. Is it independent? Are these independent events a diamond and a queen? So the probability of event A equals the probability of A given B. So the probability of event A in this one would be the probability of a diamond. So is the probability that you draw a diamond equal to the probability that you draw a diamond given that you've already drawn a queen? So how many diamonds are there in a deck of cards? There are 4 diamonds. There are not 4 diamonds, there are 13 diamonds. Sorry, I was thinking about the number of queens there. There's 13 diamonds, so that's 13 out of 52. And the probability of a diamond given a queen was 1 over 4. 13 over 52 will reduce to 1/4, I believe. Sorry, I had to double check. It does reduce to 1/4. So these are independent events. So the probability that you draw a diamond given that you've drawn a queen and the probability that you draw a diamond are independent events. So that makes these two things independent of one another, meaning this one does not have an impact on this one. The last example, example number 7, goes back to that same chart we had in example number 4. So let's go ahead and fill in the numbers that we filled in just a second ago so that we've got those on hand, because it makes everything go a little bit faster if we've already got those numbers there. So a survey of 110 high school students asked them whether they prefer dogs or cats as pets. So now the question is, what is the probability that a student chosen at random prefers cats? And are these independent events? So when we look at this, a student chosen at random is a junior who prefers cats. So the first part we want to know is, are we talking to a junior? So that needs to happen first. And then we want to know, hey, does that junior like cats? So does someone like cats given that they're a junior in high school? So to determine that probability, we're going to say the number of people who like cats and are a junior in high school divided by the number of people who are a junior in high school. So we look at our chart, we find where our cats are at. Here are our cat lovers. Here are our juniors in high school. Those two things intersect with 6 people. So we're going to say 6 divided by the number of juniors. There are 28 juniors. So 6 divided by 28, which reduces to 3 over 14. As a decimal is 0.214. So as a percentage is 21.4% of the people surveyed liked cats given that they were a junior in high school. So then the actual question here, or the second question in this case, is, are these independent events? So we're going to take that, the probability that someone likes cats should equal the probability that someone likes cats given that they're a junior. If those two things equal one another, if those two probabilities are equal, then we have independent events. So the probability that someone likes cats, how many people like cats? 22 people like cats out of 110 people in our school. And we've already calculated this as being 3 over 14. There's a couple of different ways you can check to see if these two fractions actually equal one another. I like to just do it as a pair of decimals. I like to take that and I like to say 22 divided by 110 is 0.2, and 3 divided by 14 is not 0.2. These are not exactly the same. They're a little bit different. And so going by the rule that we have, saying that these two things have to equal one another, we would say that these are not independent. Remember, for them to be independent, we need to make sure that the two parts of our problem are equal to one another.